All right, let's begin. I guess someone was really afraid of the quiz, decided to pull the fire alarm. Joke's on you guys, because I wasn't going to give you a quiz today anyway. So the only thing that's going to happen now is I'm going to have to rush through the lecture to make up the time that I would have had normally. So let's actually go. Let's actually move on. That being said, what I did do is not only did I give you guys one quiz today, I gave you guys 4. So I just updated the class website. What I did was I put down 4 mock quizzes. So just quizzes that you should take on your own time to just test how much you know. So there's a mock quiz 9, 10, 11, 12, and the first 5 minutes of class would be me announcing that. So I guess now that's where we are. So I'd rather just use the rest of class time on lecture material and just to make sure that we have things down as opposed to wasting more time on quizzes. So I put, like I said, mock quizzes online. Take them during your own time. For best results, take them as if they were quizzes. Just sit down and pretend you were doing a quiz. And I mentioned the topics for each one. So the fake quiz 9 covers linearization, differentials, related rates. The fake quiz 10 would cover critical points, absolute extrema, and the mean value theorem. The fake quiz 11 will contain curve sketching, and the bonus section is on optimization. And quiz 12 will cover the basics of antiderivatives, which we actually covered last class. So give yourself around 15 minutes each. Maybe for the curve sketching one, you can give yourself 20 minutes. But do that, and I posted the answers there as well, so you can test yourself and then check the answers when done. That being said, I just want to move on with the lecture now. So we're going to continue the discussion we started last time with antiderivatives. Area. Area. So last time we looked at the solution to the area problem, which was a very archaic solution. The idea was you take something, you slice it up into a bunch of little shapes that you know how to find the area of, and you add up the shapes. So we can approximate area of irregular shape by summing smaller known areas. Right, so that was the idea behind the solution to the area problem, but as you can see, that's quite tedious and it's not very formulaic at all. So if someone gives you a new shape, you just have to slice it up again and start all over. There's no real theoretical background that can help you actually do this process a lot easier. At least there wasn't for a long time. And so what we're going to do now is try to figure out how to solve the error problem a little more elegantly, something befitting 20th century people. And one thing that's important, obviously, need to be good at summing stuff up. And so enter series and the sigma notation. Which I believe your textbook talks about this in, I want to say 5.2. Normally they put something like this in the appendix of a calculus textbook, but your textbook actually dealt with it in chapter 5. So 5.1 was talking about the error problem and this kind of idea, and some ideas that I'm going to talk about now. But then in 5.2, it teaches you about series and sigma notation. So here's how that goes. Let A1, A2, A3, AN be a sequence of real numbers. A sequence, that means a list of numbers in a definite order. So you can write down a list of numbers in a certain order. There's a first element, there's a second element, there's a third element, there's a fourth element, listing up to n elements, let's say, and we call such a list a sequence, right? Whenever we have a list of numbers that goes in a very specific order, maybe according to some formula, we call that a sequence. Now, what a series is, you see me mention the word series there. A series is the sum of the terms of a sequence. And the notation, this is called sigma notation, is the following. You have the Greek letter uppercase sigma, pretty much the equivalent of the letter S for sum, and you can say, okay, I want k to go from 1 up to n of things that look like a sub k. So you can think of a sub k as telling you the formulas that gives you each number, and I want to add up all the things where k starts from 1 going up to n. So basically what this means is I want to take a1, plug in k equals 1, plus a2, plug in k equals 2, plus a3, and so on and so forth. I want to add all these things together. And this is a nice way that you would write that down. It's called sigma notation. The thing down here is called the index. And this number here tells you the starting point. And the number up here tells you the ending point. And this symbol here is called sigma. And so this is just some term that represents all the members of the sequence, and this symbol means I want to add them all up. So that's called sigma notation. So here's an example. I can tell you about the members of some list that I'm thinking about. A sub k equals k plus 2. That gives you a formula on how to find the members in the list. And I want you to find the sum of ak, where k starts at 0 and counts up to 2. So basically what this would mean is that k goes from 0 to 2. Of ak, well that's just going to be a sub 0 plus a sub 1 plus a sub 2. And that basically means, what does a sub 0 mean? Well, a sub k means you take k plus 2. You can think of it as if it were a function. In fact, exactly that. You can think of it, it's exactly as a function. It's like I have a of k. So another way to think of the sequence, which you don't have to get that sophisticated for Calc 1, it's just a function that goes from the whole numbers or the counting numbers to a real number. And so what this means is a sub 0 means I'm going to plug in k equals 0. Plus a sub 1 means I plug in k equals 1. Plus a sub 2 means I plug in k equals 2. So what this means, this would be 2 plus 3 plus 4. And that would be 9, the answer to that and 9. So this notation here just basically means I'm adding up a certain number of terms, which goes from, it starts by me plugging in the bottom number, adding it to when I plug in the next number and the next number and the next number until I hit this number, and then I stop. Now that is not, it's important, but it's not going to be the main thing that we care about, and you'll see why in a second. But note, it is possible to have an infinite list and to make sense of its sum. So, for example, I can have a formula that is giving me a bunch of numbers and it just keeps going. Like the list just keeps going on forever. So, given A1, A2, A3, and it keeps going, right? There's some way that I'm generating a bunch of numbers in a list that just keeps going. And we can talk about the idea of adding up all of these numbers to infinity. Which means I'm going to take A1 plus A2 plus A3 plus, and keep going. Right? And I keep adding them forever. This is called an infinite series. And it turns out they often add up to something. Well, I shouldn't say often. Sometimes. They add up to something. Something meaningful. Okay? Which might seem like a weird thing to actually occur, right? So basically, I'm saying that, yes, even in the case that all your a sub k's are positive real numbers, you can add up an infinite number of positive real numbers and somehow come out with a result. You can come out with like 5, or 2, or 1, or pi squared over 9. Like sometimes you can add up an infinite number of things and you can actually come up with a finite answer. And that may seem strange to some of you. It seemed strange when the idea was first thought up of. But then you have things like Zeno's paradoxes, which kind of made people start to realize that, yeah, it's not really a paradox. There must actually be a way to actually get this done. So one of Zeno's famous paradoxes was, imagine that you were, I forgot what the actual distance was, but let's say you were a mile from a target and you have a very powerful arrow, a bow and arrow, that could actually hit a target from a mile away, right? And so you aim at the target and you release the arrow. And so Zeno says, well, there's a way that we can think of the motion of the arrow to be like the following, right? So we can kind of freeze time when the arrow is half the distance away from the target. And then we can freeze time again when it's another half of the remaining distance, and another half, and another half, right? So you can fire the arrow. Once the arrow has traveled half a mile, freeze it, okay? So it's now traveled a half a mile. If it travels another quarter of a mile, freeze it then. Okay, now it's traveled a quarter of a mile. If it travels an eighth of a mile, freeze it then, right? And what you can think of this as, you can dissect the motion of the arrow by saying, well, it has to keep covering half the distance until it gets to its target. And then you start to think about, well, what would it mean to add up all these distances? What would it mean to take a half, plus a quarter, plus an eighth, plus a 16, plus a 32? And then you sort of think, well, if it's always traveling half the distance towards the target, it must never hit the target. These numbers must add up to infinity. But then, of course, reality tells you that no, that doesn't actually happen. these numbers must add up to 1, right? They have to add up to 1. The target is 1 mile away, and I'm just talking about the distances the arrow needs to cover to hit 1 mile. Eventually, the arrow does hit the target. It's possible to add up an infinite number of numbers and somehow come up to some meaningful result. There's no way that the answer could be larger than 1 because you would pass the target. And there's no way that it could be smaller than 1 because the arrow doesn't stop in midair. The arrow eventually hits the target. So there must be a way of adding up an infinite number of things and somehow coming away with an answer. Now that doesn't always happen, but sometimes it does. And in the case of this thing I just mentioned, adding up a half plus a quarter plus an eighth plus a 16. And if you keep having these numbers, you can add them all up and you'd actually get to an answer. You will talk more about that in Talk 2, where you will talk about series in a much greater detail. But I just want you to understand that this idea, the idea of adding up an infinite number of things, is a thing that technically you can actually do. And series and sigma notation is going to help us how to do it. And you're going to realize why we need to be able to do this pretty soon. But that's the idea. So what does it mean? Well, there's the idea of a partial sum. The nth partial sum Sn, that's the notation for it, of a sequence is the sum of the first n terms. Okay. So let's say I have a sequence A1, A2, A3, A4. It could be finite, it could be infinite, it doesn't matter. What I can talk about is, let's take the sum of the first term. I can call this S1. That is the sum of the first term. And I can talk about, let's add the first 2 terms. I would compute that result and I would call that S2. Let's add the first 3 terms. Then I would compute that result and call that S3, and so on and so forth. I can add the first 4 terms. This is S4. I can add the first n terms. And I call this Sn. This is what the idea of a partial sum. Now what you will notice about a partial sum, and you can look at this for the finite case. You'll notice that the SNs will approach S, right? So, I don't know, silly example. Let's say I wanted to add 1 plus 2 plus 3 plus 4 plus 5, right? So, I can start by adding 1. S1 equals 1. Then my S2 would equal to the sum of the first 2. That would be 3. Then my S3 would equal to the sum of the first 3. That would be 6. Then my S4 would be the sum of the first 4, that would be 10. Then my S5 would be the sum of the first 5, that would be 15. Now what you'll notice about the list, 1, 3, 6, 10, 15. So here I'm thinking of an original sequence where A1 is 1, A2 is 2, A3 is 3, going all the way up to A5, which is 5, right? And now I'm talking about adding up the guys of those lists. I could create another sequence. This is called the sequence of partial sums. This is S1, S2, S3, S4, S5. It's called the sequence of partial sums. I'm kind of rushing through this because in Calc 2 you're actually going to deal with this a lot. So this is called a sequence of partial sums. So given some original sequence, I can create another sequence from that sequence. It's just the sequence of me just adding up a certain number of terms, and then what you're going to realize is that the actual answer, S, the sum of all of these numbers is 15, and what you'll notice about these numbers is that they continually increase until they hit 15, right? So you can see that this would work for a finite number of terms, and basically, when we talk about an infinite number of terms converging to a number, this is going to be the idea that we're going to use to figure out that that actually happens. So, you may find the following. So I can talk about if I have a sequence, a series of numbers going off to infinity of a sub k. So I'm adding a1 plus a2 plus a3 plus a4 plus a5, going on forever. Okay? How can I actually make sense of this? Well, first of all, I'm going to think of this as first adding up the first n things, right? And I know that that is going to be equal to S sub n at some point, right? So I'm creating a list that goes up to n terms long, which is S1, S2, S3, S4, S5. And then eventually when I add up all these guys, I'm going to end up with Sn as one of the final terms, like S to the 5 here. And now the idea is, I know eventually if I just keep going, I'll eventually hit the answer for the final sum. And so eventually what we know is going to happen is that this will hit S if the answer exists. And how would I actually figure out that if it would hit such an answer? What does it actually mean for Sn to go towards S? Like, how can I say that mathematically? Limit. It's the limit again. It's a limit. So remember when I told you about calculus really being the study of limits? I mean, most people think of it as the study of derivatives and integrals, but really, they're both going to be limits. Everywhere we're using a limit. Every time you try to do a calculus idea, a limit is going to be involved somewhere. So basically what we're going to think about is we're going to take the limit as our n is approaching infinity, right? So just let the list keep growing. This is the list that's tracking up what we're adding up to. Just let that list go and then see what it converges to. So I'm going to take the limit of partial sums. And if there's an answer to the sum of this infinite number of numbers, that limit is going to converge to that number. So when we want to take an infinite series, this is how we think about it. It's just a limit of partial sums. If I can compute that limit, then it means that this infinite number of terms actually adds up to whatever that limit is. Now this sequence here, notice that it is different from the original sequence. This guy is a formula that tells me about adding up the first n terms of that guy. Right? So given a sequence, if there's a way for me to figure out what does a formula look like when I add up the first n terms of that sequence, I can take a limit of that expression and I can actually find the answer. Now, if this limit goes off to infinity, it means then it doesn't add up to anything. There's no meaningful answer, it just goes off to infinity. Right? But if it adds up to one number, then you will realize that that has to be the answer. So if I thought of this as being the list a half, a quarter, an eighth, and so on and so forth, it turns out that you can find a formula for how those add up. And if you take the limit of that formula, you'll actually get 1 to be the answer. If you're curious about that, wait till count 2. But I'm not going to talk about that. I just want you to get the overall idea. Now, at first, we're going to spend a while talking about finite sums, just for you to get used to the idea of adding things up. But then I'm going to introduce the idea of the infinite sum in an example, and then we'll kind of use that to attack the error problem. I wanted to give another example here. Let's go to now, the notation isn't going to be very useful unless it cuts down some work for us. So let's actually figure out some ways that it will cut down some work. For example, if I wanted to add n things, right? So I'm doing a finite sequence here. And here's how the n things look like. They're all constants, right? So C is a constant. What would that actually add up to, right? So if I see this expression, the sum for as k goes from 1 to n of ak equals a constant, what would that actually mean? Well, it turns out that that would be c times n, right? And you'll see the point of this soon. We're building up to it. Why? Well, go from k equals 1 up to n, and the formula for this term of the sequence is always c. Well, that just means I'm taking c plus c plus c plus adding up c. This is when I added for k equals 0, k equals 1. I got 1 here. K equals 2, k equals 3. For all of them, all the way up to k equals n, I will be doing that. What you realize here is I have now have n c's, right? So that's just n times c, or c times n. Okay. So if I want to add up n constants that all have the same value, well, I just actually take a constant, multiply by the number of times I want to add it to itself. That one kind of makes a lot of sense. Here's another formula that we're going to want to know, though. What does it mean to add up something like this? K. So if a sub k is equal to k, much like the sequence that I mentioned earlier. So when we're at k equals 1, ak is 1. K equals 2, ak is 2. K equals 3, ak is 3. K equals 4. We add this up until we hit n. In other words, this is equal to the sum of the first n positive integers. What's that equal to? Right? So if I wanted to say, oh, what is the sum of the first 1,000 positive integers? Right? Like if I were to add 1 plus 2 plus 3 plus 4 all the way up to plus 1,000, what would that equal? Now, you could sit there and add these all up. Or you could be a little bit like Gauss. So there's a very famous mathematician called by the name of Carl Friedrich Gauss. He's one of the famous mathematicians, you know, like he's one of those heroes of the profession. People think of him kind of like they think of Einstein or Newton or Euler. So he lived, I don't know, 200 years ago, maybe 100 years ago, somewhere like that. But legend has it there was a story of when he was like 3 years old and he was in preschool or whatever. And they were just learning how to add stuff with pebbles, and you know, if you have 3 pebbles plus 2 pebbles, how many pebbles do you have now? You know, and they'd have counted all 1, 2, 3, 4, 5. Okay, so on a particular day, his class was being very rowdy, and the teacher was like, "Everyone, quiet down, shut up. I want everyone to add all the numbers from 1 to 1,000 right now." And now if you're a preschooler, that's going to take you, come on, like, oh man, and then everyone started 1 plus 2, and they're pebbles, and they're trying to figure out, well, if I wanted to push one more, what's that going to be? So the entire class is quiet because they're all trying to add up all the numbers from 1 to 1,000, and in like 2 minutes, Gauss comes up, this is the answer. It's like, how did you do that? Well, here's how he did it, which is what we're going to use to figure out the answer to that question. Here's something the little tyke figured out at 3 years old, according to legend. I don't know if it's true, but it's totally believable that this guy could do it. On a side note, I have a friend, her daughter's like 2 years old, she knows all her timetables up to 12 times. So like, how do you do that? Like, I don't know. So if she could do it, Gauss could definitely do this, what I'm going to talk about. Okay, so what he did was, he actually wrote down, like, little did his teacher know, at 3 years old, Gauss already had algebra. He had algebra skills, right? So he kind of thought about it this way. Okay, so teacher wants me to add up all of these numbers, and that's going to be S. Here's something that he noticed. Well, if you add 2 plus 3, it's the same as adding 3 plus 2. The order that you add things don't really matter. So what he decided to do was to turn the numbers around. Notice that if you put 1,000, 999, 998, 997, and this would be 3, 2, 1. So that's just another way to write the same number. But here's something that you would notice. What happens if you add 1,000 in this one? You get 1,001, right? What if you add these two? You actually get 1,001 again. Adding these two. You get 1,001 again. Notice that what this is, you'll always get 1,001, 1,001, 1,001. Now, if you add up all these 1,001s, what are you going to get? Well, 2s, of course. How many 1,001s are there? Well, there are 1,000 of them. And so, your s must be equal to 1,000 times 1,001 all over 2. So that's just 500 times 1,001. And you just multiply that out, here's the answer. It turns out you can do a similar thing to figure this guy out. Similar, if you have 1 plus 2 plus 3 plus to n minus 2, n minus 1, n. And you want to know what does all of that add up to? Well, you can actually write this backwards. What you will notice is that you get 2 times the sum would be, you add this, you get n plus 1. That would also be n plus 1. That would be n plus 1. You'd have n times n plus 1s, which means the sum here is that. And that leads us to the first real sophisticated formula. The last formula I just gave you was kind of obvious, but this one not as obvious. You do have to do a little bit of work for it. So this brings us to formula 2. If I want to add up the first n positive integers, the sum is going to be n times n plus 1 all over 2. So what is the sum of the first 1 million integers? 1 million times 1,000,001 divided by 2. You do that multiplication, it's the same thing as if someone were to be there adding up 1,000,000 numbers. Right? Now you can of course see the power of this technique. This expression literally means to add up n terms, and n can be however big as you want. But you can have a nice formula for it. right? We can be very efficient with the way we're adding things. Now, there are some more formulas that we want to know. And these I'm not going to prove for you. You prove them using something like mathematical induction. This is the typical way to actually do it. But what if you wanted to talk about the sum of the first n squares, right? So this means like you're adding up 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to n squared, right? Out of the first n squared terms. Turns out that that is going to be equal to n times n plus 1 times 2n plus 1 all over 6. It's a very important formula. You have to have it memorized. All the formulas that I'm giving you, you should have that memorized. So that's another one. So if you want to add up the first n squares, that's what it's going to add up to, right? Another one, the first n cubes. So you're adding up like 1 cube plus 2 cube plus 3 cube, all the way up to n cubed. What does that add up to? Well, curious enough, it adds up to what the first n terms added up to squared. That would actually be what it sums to. Should know that. What about the first n? That's where we're going to stop. We're going to stop at the cube formula. Okay? So you need to know how to add up n constants, how to add up the first n positive integers, how to add up the first n squared integers, the first n cubed, the first cube n. You get rid of these. The first n cubed integers. Yeah, I think that's how you'd say it. Instead of cubed, say cubed with a D. Okay. So we have all these formulas, these nice formulas. You'll see where we're going to use it in a bit. Don't worry about it right now. But in the meantime, let's actually do properties of sums. Two important ones. You must also know one. Suppose I have a sum of a bunch of terms, but I multiply those terms by a constant. It turns out that I could equivalently factor that constant out and multiply and find the series after, right? So one property that's an important property of series is that you can factor out constants. It's kind of like how you can factor constants outside of a derivative, and you can factor constants outside of a limit. Why is that true? Well, if I have the sum of C, A, K, K goes from 1 up to n. That means C times A1 plus C times A2 plus C times A3 plus all the way up to C times AN. But because C is in everyone, this is just a regular sum. You can factor A1 plus A2 plus AN. And then you realize that a nice way of writing that is just the sigma notation AK. So you can factor constants out of series. That's a very important thing to know. Here's another thing you want to know. Series actually distribute across sums. So if I had the series of some formula plus or minus some other formula, then this is actually going to be equal to the sum of the first one plus or minus the sum of the second one. why would that be the case? Well, if I have the sum of AK plus BK, that's going to be A1 plus B1 plus A2 plus B2 plus all the way up to AN plus BN. But this now is just a regular list of the sum of terms. We know that addition, we don't care about the order. So what I could do is I could just decide to add the A's first and then rearrange so that I add the B's second. But this just means the sum of AK, and that just means the sum of BK. So a series will distribute across a sum. You should know they do not distribute across products. So if you have a sum of AK times BK, it is not the same as summing AK and summing BK. That's not going to be true because that should be obvious. But why? Because if you look at the sum of AK times the sum of BK, well, that's A1 plus A2 all the way up to AN times the sum of the B's, B1 plus B2 all the way up to BN. And of course, you have to actually FOIL, right? So this is going to be A1, B1 plus all these guys, AN, BN, which is this guy. But you actually wouldn't be done. You have to actually add a bunch more terms. You have A1B2 and A1B3, and you have a bunch of other terms that are not accounted for in this list. So this expression cannot equal to that expression because you need this expression plus a lot more things to add up to that expression. So it does not distribute across products. It does, you can factor constants out, and it distributes across sums. Let's do some examples. Find the sum. Let's do 2. Say I wanted to add up a bunch of things that looks like that. Say K goes from 1 to 50. And let's say I wanted to do this. K goes from 1 to infinity. And I wanted to add up terms out like that, an infinite number of terms. We're going to see how that works. Don't really have the time to like think about it because fire alarm. So let's actually just jump into this. How would you do that? Well, I would use the two previous properties. I would be able to realize that this is just the sum from 1 to 50 of 2k cubed minus the sum from 1 to 50 of k squared plus the sum from 1 to 50 of the constant 1. And here I would be able to factor out a 2. Here, well, I don't need to anything. That's actually in a nice form. And here we have that. Now what you'll realize is that we actually have formulas for these guys to sum the first cubed things, the first 50 cubed terms. This is summing the first 50 squared terms. This is summing 50 constants, each having the value of 1. We have formulas for that. So this is going to be 2 times n times n plus 1 times 2n plus 1 all over 6. This one is going to be, that's the cube term. So that's going to be n times n plus 1 all over 2 squared. This one is going to be n times n plus 1 times 2n plus 1 all over 6. This is going to just be 50 times 1. And what you can do here is, you just add those all up. Now, what I want you to understand what you're actually doing is you're taking a bunch of terms by just multiplying these out and adding these 3 things. What you're doing is you're adding 50 things that look like this. So the summation notation actually allows us to add things very efficiently, very quickly. I can add up 50 things that that are complicated individually, and I can get to the answer by adding 3 things. So what you'll notice is what we're doing is it's like we're taking 2 times 1 cubed minus 1 squared plus 1 plus 2 times 2 cubed minus 2 squared plus 1 plus 2 times 3 cubed minus 3 squared plus 1 plus 2 times 4 cubed minus 4 squared plus 1, and we keep doing that 50 times. What does that add up to? Well, it's going to add up to whatever this is. And by comparison, this is actually not going to be that bad to actually calculate. So I can add up 50 things of 3 terms each by adding up 3 terms. So that's really nice. It allows us to add things very efficiently. You're going to see how this applies to the area problem pretty soon, but for now I just want you to know that we can do this, right? So if you're going to want to pay someone to sit there and add up the areas of rectangles, at least give them an efficient way to do it so you don't have to pay them overtime, right? So we can have a very efficient way of adding up a lot of things via sigma notation. Now, what would B look like? Now this one, we want to add up an infinite number of terms. What does that mean? Well, this means just add up n terms at a time. And then let n go off to infinity. Not necessarily this number. Just use uppercase n. So now we have to add up an expression that looks like this. How can we actually do that? Well, I'm going to use the properties again. Notice that the summation, the variable for the summation is k. So that should have been something that's noticed. K is the variable for the series. K is the thing that's changing. I'm going to plug in k equals 1, then k equals 2, then k equals 3, all the way up to n, and I'm going to plug that in. I'm going to add those all up, which means anything that's not a k as far as the series is concerned is actually just going to be a constant. So, in other words, the small n compared to the series, in relation to the series, is actually a constant. So, what I'll realize I actually have is going to be the sum, k goes from 1 to big N of, I can write this as 1 over n cubed times k squared. If I just multiply that out by the laws of exponents, that's going to be equal to 1 over n cubed times the sum of k squared. I think I did want a small n here. So you can see why this is going to. Because it doesn't really matter how many terms I start out with. I'm letting it go off to infinity. So what we'll have here is, we actually know what this expression is. This is n times n plus 1 times 2n plus 1 all over 6. So in other words, I end up having to compute a limit, n times n plus 1 times 2n plus 1 all over 6n cubed. What is that limit? Third. You have to remember your limits. So that's one of the ratio of leading coefficients idea, right? I just had one polynomial divided by another. The highest power on the top and the bottom were the same. So the limit as you go off to infinity is the ratio of the leading coefficients. The numerator was just 2n cubed plus a bunch of terms that I don't care about, because all the lower terms won't matter if I'm going off to infinity. So I have something where the highest, the leading coefficient and the leading term is 2n cubed, divided by something where the leading term is 6n cubed. And of course, because the leading terms have the same powers, the limit goes to the ratio of coefficients, so that's actually 1/3. So what does it mean to add up an infinite number of things that look like this? Well, it means to add up to 1/3. So in other words, this is what I would get if I decided to add 1 over n times 1 over n squared plus 1 over n times 2 over n squared plus 1 over n times 3 over n squared plus, if I keep doing that forever, what is that going to add up to? Adds up to 1/3. Now this might be all be confusing, I understand, but take some time to sink it, so don't worry too much. But you will need to know how to actually do this calculations. Both the finite and infinite case, and a lot of it comes down to you knowing those formulas that I mentioned before, knowing how to add up the first cube terms, the first square terms, the first n terms, so on and so forth. And if you had to add up an infinite number of terms, pretty much you're going to think of it as a limit of adding up a certain n number of terms. Applying the formulas and then taking the limit at the end, which you have to remember all your limit rules from way back when, you can get to the answer. How does this all help us? All right, let's go back. So that was just a small excursion in series, and like I said, it's going to be a big topic in Calc 2. If you take the 212 version, which is, I think everyone here has to take that version. Okay, what does that all mean? Back to the area problem. That was an important detour. We needed to find an efficient way to add things up, because to solve the area problem, we're just going to have to add a bunch of things up. So we don't want to spend forever or be like Archimedes, just literally counting and adding up areas. That is actually too tedious. So we need an efficient way to add stuff together, and so now we can actually go back and look at the area problem in a more sophisticated way. So remember what we wanted to do. So you start by doing the following. Here you have some irregular shape. What you can do, you can slice it up. I can add up the areas of all these rectangles. That's like me adding up a bunch of numbers. So I can actually describe this by a sequence. I can say, this is the first piece, the second piece, the third piece, the fourth piece, the fifth piece, etc., right? And I can just let AK be the area of the kth rectangle. And so basically what I'm interested in here is the sum of all the AKs. Now, that is a little bit too hard. Because how would I actually describe this pattern? Well, if I want to get a formulaic way of doing this, I'm going to start to have to number all the vertical lines, which I would use one variable to do. So maybe K should be the vertical line. And it turns out that mathematically, I would also need a way to track how many horizontal lines I need. And I would need a whole other variable. I would need something like L to track the horizontal lines or something like that. That's too hard. Not too hard in general. When you get to Calc 3, you're going to do exactly that, this kind of idea. But in Calc 1, we only want to deal with one variable. So better to do this. So you have that same shape, but now I just slice it into vertical strips. And so now what I'm going to do is instead of taking boxes, I'm going to take vertical strips. But these strips have very irregular shapes themselves. So kind of what I would do is create the boxes by where this vertical strip hits the shape. And so what you'll notice here is that I can go from all these boxes, which there are a lot of them, to all these thin rectangles here, right? And I could use their areas to approximate the area of the shape. Still too hard, right? I know people like to think of mathematics as something that's just complicated for no reason, but actually, it's exactly the opposite. Math is about making things as easy as possible, and these are still too hard to figure out. We want to go to a better case. Let's look at half the shape at a time. So here's what's going to happen. Here's my shape, but I'm going to slice it in two and just ignore the bottom half. Just like, don't even worry about it right now. It's just too much stuff to worry about. But I'm going to do the same idea. Slice this into vertical strips. And somehow measure rectangles that are defined based on those vertical strips. The nice thing about that is, what's nicer about using half the shape as opposed to the whole shape? Well, when you realize what I'm doing here, I just wrote the XY plane. I just put the shape on the XY plane. What's the distinction between this shape and that shape? Is that one's a function. This one is not, right? Notice that this thing here fails the vertical line test, right? I can draw a vertical line through that, and it will touch the curve in 2 points, whereas if I draw a vertical line through this, it touches the curve through 1 point. So by going from this to that makes it a little easier, but it's even better to do that because now we can think of this as a function. And so now it's going to be even nicer because we know how to deal with functions. We've been dealing with functions for years. Ever since we were little kids, it's been building up to us learning about functions, and we learned about them in algebra class, and again in pre-calc class, and then we talk about it again in calculus class. And we know how to do all sorts of things with functions. We know how to add them together, how to sketch functions, how to find derivatives of functions, how to find tangent lines of functions. We know a lot about functions. So if I can go from a situation where I'm dealing with just a bunch of random rectangles that someone has to draw in, to a situation where now the rectangles, their height is defined by a function, it gives me a lot more options to actually figure out how to deal with the situation. So this is how we're going to make the area problem nice. Instead of adding up a bunch of areas that look like this, I'm now going to add up a bunch of areas that look like this, where I can talk about those areas in terms of a function that's given to me. So, and of course you'd realize that if I knew how to deal with the situation where I'm only taking half the shape, I'd automatically know how to deal with the situation where I'm taking the entire shape. Because I would just repeat what I have for the bottom half and ignore the top half, right? And then I can add the areas together. So pretty much this is the situation we really want to know how to deal with. So we reduce the area problem to doing that. If I know a good way to find the area under some function, I will automatically know a nice way to solve the area problem. Right? Something that doesn't require all the manpower of just adding up a bunch of shapes. So this is the new problem. We're going to solve this complicated problem by solving this simpler problem. If I know how to solve this, I'll automatically know how to solve that. So let's actually see how this is going to work. How would this actually work? Now, suppose I have some function. Let's just draw a nice function. This is y equals f of x. And let's say I wanted to find the area under this curve on the interval AB. Okay? So I'm interested in this area. But of course, this function here you can imagine it's of an irregular shape. It's not a straight line. It's just some random shape here that is described by this function. How do I actually find the area under that curve? Well, we're going to start with the dissection idea. What we're going to do is we're going to dissect this interval AB into a bunch of terms. And what I'm going to do is on these subintervals, they're called, I'm going to create rectangles. So let's say here I decide to cut off the height of the rectangle on this side. So now what you'll notice is that I now have these rectangles to talk about. So we'll approximate the area under F on AB by the sum of the areas of these rectangles. That's the idea. I add up the area of these 5 rectangles. That will give me an approximation for the area under the curve. Will it be the actual area under the curve? The answer is no, because as you can see, there I'm missing some space here, right? So this is not going to actually be the area. It's an approximation for the area. Okay. So now let's make this thing nice. We're going to start putting in our labeling. A, I'm going to call x0, let's call that. And then the next section is going to call x1, then x2, then x3, then x4, and this guy here is x5, which in general you can think of B as xn. So I have x0, x1, x2, x3, going all the way up to xn. In this case, n equals 5. What I want you to notice here is that we'll automatically be able to figure out the heights of the rectangles. If I come across here, notice that this height here is from f of x0, whereas the height over here is f of x1, whereas the height over here is f of x2, height here, f of x3, and so on, right? But by the time I reach the height over here, it's f of x4. So I'm going to dissect the x-axis into a very convenient way. X0, x1, x2, x3, blah, blah. And I will be able to, if I know the formula for that function, I'll be able to plug in the x value here to figure out the height of a rectangle. Now, the distance here between this thing here, that distance is called delta x, right? For the change in x. So I can look at here as all of these are the change in x's. So here's what we can start to set up. We're going to develop a nice formula for all this. So we create n, they're called subintervals. Where we're going to start drawing the rectangles. Here n equals 5. Delta x, they all have equal width. Which we call delta x. One thing I want you to note, you can actually know what delta x is going to be if you assume that they all have equal width. Well, if I'm looking at n rectangles, right, I would want to split up the interval AB into n equal lengths, right? So how many ways can I do that? Well, I'm going to take, if I want to know the width of each one, I'm going to take the length of the whole thing and divide it into n pieces. What is the length of the whole thing? Well, right minus left, b minus a, that's how you find the horizontal distance. So delta x is actually going to be b minus a all over n. So now I have a nice formula for the width of my rectangles. The height of each rectangle is given by, you'll notice, f of x sub k for some k. Where my k can range from, say, 0 all the way up to n. Right? So it's going to be f of x0 or f of x1 or f of x2. It can be f of any of these depending on how I'm creating these rectangles. So that's going to give us the height of each rectangle. Now, here's how we are going to actually set that up. This means the area is going to be approximately equal to, well, say f of x0 times delta x. That's the length and width of the first rectangle, plus f of x1 times delta x, length times width of the second rectangle, plus f of xn times delta x, length times width of the last rectangle. Of course, you'll notice here that this is just f of x0 plus f of x1 plus all the way up to f of, well, technically this would be n minus 1 on the example that I did here, and times delta x. Now, notice how I can write this. This here is actually just a sum of numbers that go in a definite order. I can write that as a series. Let my k go from 0 to n minus 1 and multiply all of those terms by delta x. So I can say my area is going to be approximately equal to this series. Now, of course, the benefit of thinking of this as a series now means I have a whole bunch of formulas and theories, ones that I just told you about 10 minutes ago, that I can use to my advantage when trying to figure out how to add up all these things. Now, there are many ways to actually construct the rectangles. In Calc 1, we care about 3. So, on your next test for this class and on the final, they are going to ask you to do something like this in one of 3 ways. The first way that I'm going to tell you about comes in no particular order. But the first one I'm going to talk about is using right-hand endpoints. Okay. Now, what does it mean to use right-hand endpoints? Okay. So here's our function. Here's our interval. I want to cut this up into, say, 5 pieces. Right-hand endpoints means I'm going to look at each subinterval, and the right side of that subinterval is going to determine the height. So I'm going to look at the first subinterval, the right side travels up, hits the function, that's the height. Second subinterval, the right side travels up, hits the function, that's the height. Third subinterval, the right side travels up, hits the function, that's the height. Right side hits the function, that's the height. Right side hits the function, that's the height. So I can construct my rectangles by taking the right endpoints of each subinterval. This is called using right-hand endpoints. Now the approximation here is called R sub n for the right-hand approximation using n rectangles. This is of course going to be, because this here is x0, that's x1, that's x2, all the way up to xn. Notice that this is going to add, it's going to start plugging in the x1 value to the function, then the x2, all the way up to the xn. So this is going to be, k goes from 1 up to n of f of xk times f of x. So I'm going to be f of x1 plus f of x2 plus f of x3 plus f of x4 all the way up to f of xn. All of that times delta x. which we know we can actually compute that. That's b minus a over n. So that's called using right-hand endpoints. So you need to understand that as an idea because you're going to do calculations based on that. Another way, using left-hand endpoints. So we can think of the exact shape here. Again, we're going to cut this up into a bunch of things. Now, instead of taking the right side, I'm going to determine the height of the rectangles by the left side. So I look at the first. The left side comes up, it's the function, that's the height. Second, left side comes up, it's the function, that's the height. Third, left side comes up, it's the function, that's the height. Fourth, left hand comes up, it's the function, that's the height. Fifth, left hand comes up, it's the function, that's the height. So I can approximate the area of under the curve using these rectangles. This is called L sub n. And you will notice that this is k goes from 0 up to n minus 1 of x of k delta x. That's called the left-hand approximation for the area under the curve. One thing you can notice here is that using right-hand approximation gives us an overestimate for the area. Notice that the areas of all these rectangles will be actually larger than the area that I want. Whereas the left hand will give me an under approximation. And that's not in general, it's just for this particular function, right? This function is increasing, so the right side is always going to be taller than the left side. And so we end up with an over approximation from the right, but an under approximation from the left. The last way you need to know how to set something up is using the midpoint. Approximation. So how you would set this one up with the same function. Here's A, here's B. You're going to dissect it just as you did the other times. But the difference now is you're going to use the middle of each subinterval to create the height of your function. The middle to create the height of the function. The middle to create the height of the function. The middle to create the height of the function. The middle to create the height of the function. Now what would those rectangles actually look like? They would look like this. Now what you realize in this particular case is that this one is a little bit self-correcting. So you'll notice that on the left side it gives you an over approximation, but it kind of tries to make up for that by on the right side giving you an under approximation. So it kind of tries to balance itself out, which is often one of the benefits of using the midpoint. So the middle points, we label them by a new labeling. We call this x1 star, some people use x1 bar, x2 star, x3 star, so on. Here's xn star. And so the midpoint approximation would be the summation of k goes from 1 up to n of f of xk star times delta x. So, three different ways you need to know how to set up the rectangles. Using left-hand, midpoint, or right-hand approximations. In the above, of course, our n is the number of rectangles equals number of subintervals your delta x you can calculate by e minus a over n. And I want you to notice that the x sub k, how would you actually figure that out? Is you'd start at the first point, and then to go from this to that, you will add delta x. Go from this to that, you will add delta x. Go from this to that, you will add delta x. So to go from one point to the next, you're adding delta x. So if you're here and you want to know what is the fifth point's location, well, you would have to add delta x 5 times to get there. So it turns out that the subscript tells you how many times you need to add delta x. And so basically, start with a plus k times delta x. And that's going to tell you how to find the x coordinates that you want to use. So this you need to know, that you need to know, and that you need to know. And I wanted to finish this example a little more, but we have to start late today. So what I will do is I will give you the next example, and I want you to see if you can figure it out. And we'll pick up with this example next time. As well as, remember I put up 4 mock quizzes. At this point you can do all of them. I've taught you enough to do all of them. So you should actually try those on your own. Pretend they're quizzes. If you just look at the answers, it's not going to help. Approximate the area under this curve. I'm going to give you a specific curve, x squared. No, this one. 6x minus x squared. On the interval 0, 6, using 3 subintervals. And now on a test in the final, you're going to be asked for one of these, but I want to do all 3 of them with you. So you can see the difference between all of them. Right-hand endpoints. B, using left-hand endpoints. C, using midpoints. This is some random function. There's some area under that function on the interval 0, 6. That actually looks like an upside down parabola going through 0 and 6. This is the area we want to approximate. I want you to approximate that area using 3 rectangles. Construct the rectangles using the right-hand way, the left-hand way, and the midpoint way. Add up all the areas. Tell me what answer you come away with. And then, next time we'll do that, and we'll move on. You're going to need these formulas to do that. So try them, see what you come up with, and we'll pick up with that next time.